Okay, so welcome to our very first tutorial session for today, and we are going to discuss wave motion. It will be very appropriate to understand what wave motion is all about. So we kickstart that with a definition. So a wave is a disturbance which travels through a medium. Okay, so let's say uh, this we have here air. So air is a mixture of gases. All right. Now, if we are saying that wave is a disturbance, it will cause the particles of air to vibrate. Hence, the reason why we consider it as a disturbance. So, assuming this is our wave, all right, this is our wave, it will enable energy to be transferred from a source so the source can be point A to another source, or to another point, I should say, which is point B. Without the particles, these particles that the wave is traveling through also being transferred, meaning that if it has energy and is carrying, let's say, data, the data will be moved from point A to point B without distortion. I hope that is clear. Now, for waves, they can be considered as either mechanical or electromagnetic. So, mechanical wave, they require material medium for their propagation through propagation. It means that they will need to travel through matter. Okay, they will need to travel through matter before they can transfer the energy from one point to another. Okay, so having spoken about the fact that mechanical wave will require material medium for their propagation, example sound wave. Okay, so sound wave. So if I say clap, when I clap, vibrations around my palm will cause the disturbance, which will travel from the source of clap to your ears. Okay, so sound is defined as the kind of wave that is sensitive to the ear. So it means that it will travel through air. Air is also a mixture of gases, so we can say that air will fall under gaseous substances when we look at the particulate of matter. All right, so with electromagnetic wave, they do not require material medium for their propagation, meaning they can travel through vacuum. Vacuum means empty space. All right, so there is no matter. Example is X-ray. Okay, X-ray, and it's the same way the sun's uh, radiation is able to travel through space before it enters into the Earth's gravitational field, right? So the space in between. All right, so let's look at the differences between mechanical and then electromagnetic wave. So for mechanical wave, we've established based on the definition that they require a material medium for their propagation, whereas electromagnetic waves do not require a material medium for their propagation. Right. So point number two, for mechanical waves, they can be transverse or longitudinal. Okay, so emphasis on transverse And so this is transverse. I'll need to explain that to you. And also longitudinal. But electromagnetic waves can only be transverse. So we move on to the third difference, which says that for mechanical waves, they travel at a low frequency, whereas electromagnetic waves travel at a relatively high frequency. Okay, so when you are comparing two things, you need to use the word relative, because one may be higher than the other under certain circumstances. Alright. So between the two, here are the differences. Now, waves can also be differentiated by how they travel. So we are going to look at progressive waves. Progressive waves are basically traveling waves. Okay, so a wave can be either a progressive wave that is traveling or a stationary wave, meaning it is trapped in a column, usually an air column. Alright, so that is what sound wave is all about. So sound wave is about stationary wave, but here we are looking at the general wave theory, so we have to look at it in a broader perspective. Okay, so a transverse wave is a type of wave whose direction of the wave is perpendicular to the direction of the vibration of the medium. So in a graphical format, we have something like this, what I have to my left here. Okay, so to my left, so for transverse wave, the particles can move 90 degrees. If the propagation is this way, it won't be the same, but then it can be up, down, up. So for instance, if you have a scenario where uh, a string is blocked, say not uh, the string of a guitar is blocked, it goes up and down, but then the wave, as it goes up and down, will also move forward. Right. So if the travel of the wave is perpendicular to the vibration of the movement, we say that kind of wave is a transverse wave. But then if the direction of the travel of wave is the same as the propagation, let's say you have a spring, you compress the spring, then you release it. See, it travels along the same line. No bubbling like up and down or any other sort of movement. So the direction of travel of wave is the same as the propagation of the wave, then we can say that this indeed is a longitudinal wave. So one characteristic feature of longitudinal wave is that it will always go through a series of compression where in the case of a spring, where the spring comes together, then when it is stretched or released, it goes through what is known as a rarefaction. Hope it has been explained into details for you to understand. Okay, so let's look at some terminologies that are used to describe a wave. The first one is amplitude. So suppose you have a wave diagram, okay, and this is the origin, which is zero. So the particle moves from zero and gets to this stop. This stop is known as the crest. Then at the bottom, the lowest dip is the trough. Okay. So the highest point that is read on the y-axis here is the amplitude, and it is defined as the maximum displacement of a particle. So if this is the particle and the maximum displacement from its mean position, so if it is there at the mean position, it means it is at rest. So the amplitude is used to describe the maximum displacement of a particle from its mean or resting position. Now, in terms of period, we are looking at the cycle. So if 20 or 25, let's say 25 oscillations is equal to a cycle, the time that it will take for the particle to complete this 25 oscillation, which is equal to our one cycle, is what is known as a period. So for a period, we are looking at a range of oscillation being performed. Then for frequency, it's more of the inverse of the period. We are looking at the number of cycle or oscillation performed in 1 second, performed per second. And this formula here is the relationship between period and the oscillation. So the period T is the inverse of oscillation. There is also another one here that I've not captured. It's known as wavelength. Wavelength is the distance between two successive crests. So crest one, crest two, the distance is the wavelength, right? Or two successive troughs. So the distance between two successive troughs can also be considered as a wavelength. You don't take a crest and a trough. That is of the wavelength. When we put all this together, a wave can travel at a speed or velocity, okay? And at this velocity, it will travel with a certain frequency, and then it's going to have a wave length. So this is the relationship between the frequency, sorry, between the velocity of a wave, the frequency, and then the wavelength, where all the symbols have their usual meaning. Okay, so the V is for velocity, F is for frequency, and lambda is for the wave length. We are going to look at the general wave equation very soon, and then we'll discuss how it is used. So, in my earlier submission, I showed you the relationship between velocity, frequency, and wavelength. So, I have a question here to demonstrate how that equation can be put to use. So, I read the question, a wave travels a distance of 80 meters in 4 seconds. The distance between successive crests of wave is 50 centimeters. Calculate the frequency of the wave. So it is very important to extract the data from the question. Okay, as this is standard practice, and then it will help you understand the question at hand. So the wave travels a distance of 80 meters. So we can say distance here is 80 meters. Okay, and then the time is 4 seconds. 4 seconds. This will help us calculate the velocity. Because velocity is displacement or distance moved in a specified direction. So you have the displacement, in this case, the distance over time. And this is 80 divided by 4, which is 20 meters per second. So, but then in the explanation given to the definition for wavelength, we said it is the distance between two successive crests or trough. So in the question, when you say choose between successive crests of the wave, it means that is the wavelength. The wavelength is given in centimeters. In this case, 50 centimeters. So we need to convert it into meters. That is zero point 0.5 meters. But we know that our velocity is equal to our frequency times the wavelength. But since we are looking for frequency, we can divide here by lambda, divide here by lambda as well. Okay, so our frequency therefore becomes velocity over lambda. So we just slot in our values. Velocity is giving us 20, whereas lambda is giving us 0.5. And this actually is 40. The unit for frequency is hertz. So we put it there, 40 hertz. Okay, so we have a question on board here, and it's about a wave profile. So we can see how to put to use our wave equation. I need to touch on something. These are the same, but you see from this equation where we have V equals F lambda, and then if it translates into F equals V over lambda. Okay, so this portion which is V over lambda is what is giving us F here, right? So when you are given such a question, it is appropriate that you pair the wave equation, the general wave equation, with the equation that has been given to you, right? So if I decide to use this equation, say the first one, okay, so y equals a sine, so 2 pi v t over lambda minus 2 pi x all over lambda. Then you write your wave profile of the question that is given. All right. So a sine 200 pi t minus pi x over 17. So this is what you do. We are looking for lambda. So there's lambda here, there's lambda here as well. Okay. But you see, we are going to compare the various sides of the equation. We don't know wavelength. We've been asked to calculate wavelength. Same time, we don't know velocity because the question has asked us to calculate velocity. So we use this side of the equation, the one on the right side. Okay, we use that side because it has only one unknown, that is the wavelength. So we can say that 2 pi x over lambda is equal to pi x over 17. So 2 cancels, sorry, let me repeat this again. So pi cancels pi, x cancels x. So our equation therefore translates into 2 over pi 1 over 17. So the rest is mathematics. We do what is known as cross multiplication. Okay, so 2 times 1 equals 2 times 17, I should say, equals lambda times 1. This gives us 34. This gives us lambda. So And then we can say that lambda, which is our wavelength, is 34 meters. So this is how you perform calculations and then finding the missing variables using the general wave equation. So we are done calculating for the wavelength. Now, same scenario. So you don't need to rewrite the equation again. We are looking for velocity. This side of the equation has velocity. So we can compare it to our other side of the wave profile given. So we say 2 pi vt all over lambda equals 2 pi 200. Think I didn't write the correct question. Yeah, that's it. 200 pi t. But we know that our lambda, which is our wavelength, is 34. So we can fix that in 34. This gives us 200 pi t. It still remains 200 pi t. T cancels this t because they are on opposite ends. Lambda also cancels lambda. So I have 2 over 34 equals 200. 2v, sorry, over 34 equals 200. So I can multiply here by 34, multiply here by 34 as well. This goes away. So 2v equals 3, 4, sorry, equals 3400. Divide here by 2, divide here by 2. So our v therefore becomes there's a mistake with the calculation here. Hold on, let me rectify it. This will give us 64. 00. So this is 3400. So V is 3400 meters per second. So the rest of the calculation we can use our previous formula, which is V equals F lambda, to take care of it. Because if we are looking for frequency, frequency therefore becomes V over lambda. Our V is equal to 3400 over lambda, which is 34. So this cancels this, and then our F is 100 hertz. Then we know that, let me squeeze this here. Frequency is 1 over T. Frequency is 1 over, sorry, frequency is 1 over T. So our frequency is 100 hertz over T. So we can say that our T equals 1 over 100, and T gives us 0.01 seconds. I hope this clears out how to solve problems using the general wave equation. I was a bit all over the place. I'm still recording from work, so I get a little bit distracted. But if you have any question, you can push them in the comment section and then I'll answer them accordingly. So this is all about the general way of preparation. See you in our next lecture. Bye.